Hi, welcome to video on LTSPICE. In this particular video, we will see how do we simulate a different circuit and how do we analyze the circuit with respect to different analysis. Okay, I think all of you are now in a position to write the circuit diagram, edit the values, and now you are supposed to do the analysis. Now, as we know that this is a common source amplifier with input given over here, and I have to take the output here. So since we know that this is the input and the drain is the output point, so first and foremost let us write the nodes as output. Maybe you can write it as V0. Okay, this is the node. I can place it here. Maybe I'll just place one more node, which is the input here. Let me edit this to V in. Now let me connect that to this node. Unless I connect, it will not be useful. Now fine, so this is V in, this is V0. Now before we actually see the response of the circuit, I have to see whether all DC conditions are matching as per my design or not. So because when you actually rig up the circuit diagram, you have already designed the value of drain current that should flow, and what is VDS, what is VGS, all those things. So which I can able to see it. If I do, I can see this is the simulation command possible. So we have this particular simulation command, which is DC operating point, will actually compute DC operating point, treating all capacitance as open circuit and inductance as short circuit, if at all, if it is there in the circuit diagram. So now if I say okay, now it has been placed here. Now if I run, so if I run, it will actually give different nodal voltages and current flowing through each of the terminal. You can see now the current flowing through the drain of the MOSFET is 1.5 milliamperes, and there is no gate current, and there is a bulk current of almost less than picoamperes, and this is negligibly zero, and we have the currents flowing through different capacitors and resistors. So if you can see, capacitor current is almost 10 power minus 20, which is zero here because no DC current will flow. So what all things that are mentioned here are all DC parameters. Now this is one thing you can observe. One more other thing you can observe here is okay, now let me just give some value also here. So maybe for doing the DC analysis, this value may not be required because this capacitor will be treated as open circuit. Still, without this, I can able to see what are the DC conditions of this MOSFET. So I can go here, I can just go to this SPICE error log, and this is what you are looking at. You can see all these different parameters of this NMOS transistor. What is drain current, what is VGS, what is VDS, what is bulk to source voltage, what is threshold voltage, what is VDS at, what is the transconductance, what is GDS. All these things are listed. So maybe before you start simulating this, you would have already calculated all these parameters. Now before you proceed with the other analysis, you can first verify whether all these parameters are as per your paper design or not. Once your paper design is matching with this, then you can go for the next possible analysis, whether it can be transient analysis or the frequency analysis. I hope of course these are the values that we have expected, and we are getting all these DC currents and DC voltages and the transconductance. Now once you are satisfied with this, now I want to see the transient response of this. So now I know that transient response is how does this circuit, that is CS amplifier, will respond for an input sine wave of certain frequency with certain amplitude. So now I will edit this source Now this source has to apply a sine wave, so I will go for this advanced option. If I go for this advanced option, now these are the possible signals you can apply, you can get from this power supply. So now this is an independent voltage source. Now it is named as Vin. That's what is this Vin here. So actually this is that Vin, so it's not this one. So let me select this V sine. So I'm not supposed to give any DC offset here, so don't edit that, and you have to give an amplitude of any amplitude of your interest, 10 millivolt. Let us give a frequency of maybe 10 kilohertz. So this is 10k is fine. So this is not case sensitive. Even if I write small k, it is 10 power 3. Even if I write capital K, it's 10 power 3. Here milli, this m, even I can type it as capital M, it will be still 10 power minus 3. So don't be under the assumption that capital M is mega. So in LTSPICE, if you want to specify milli, it is M letter, whether it is small letter or capital letter, it doesn't matter. If you want to specify mega, then you have to say MEG. So this is mega. So of course now I should not give megavolts. Let me give 10 millivolt as the input amplitude. Now I have applied an appropriate sine wave to see the response of this amplifier. So now I have to see the input waveform and output waveform, for which I have to do a transient analysis. So now let me go to the simulate, and I have to edit the simulation command. Earlier the simulation command was .op, which was corresponding to finding the DC conditions. Once we are satisfied with that, I'm going for changing that DC operating point to a transient response. Now this transient response, I need to edit these parameters. So it is asking for what is the stop time. So this stop time is 1. Now we know that we have applied a sine wave of 10 kilohertz. We also know that for 10 kilohertz sine wave, the time required for one cycle is 100 microsecond or 0.1 millisecond. So 0.1 millisecond is the time required for, okay, let me write it here. So it is, okay, 100 microsecond is the time for one cycle, time for one cycle. Okay, now so this is just a comment, this is a text. So this is 100 microsecond is for one cycle. So now let me just write it as one. Okay, let me just write it as one cycle. Now if I want to see 5 cycles of the waveforms, so then it should be, the stop time should be 5 times of one time required for one cycle. So that means I have to go here for my simulation command and type this as 500 micro, 500 U. Of course we know that micro is represented using U. Now what does this 500 mean? So this will actually simulate the circuit for 500 microsecond. If you are seeing the output or input, you can see 5 cycles. Now time to start saving data. You start saving the data from initial 0 second. So this is, I'm starting it from 0 second, and this maximum time step is, so let this be 1 microsecond. So this should be very small, meaning for every 1 microsecond this simulator will take the value and put it on the waveform display. So this should be very small compared to this. Now this is done. You can see now once I made this, okay, dot tran is for transient analysis. This is my start time up to what you are, this is start saving data from 0 second. So you are simulating it up to 500 microseconds so that you can see 5 cycles. And of course you have this one as what time step. So this 0 actually corresponds to, you can see this is dot tran, this is stop time, this is okay, this is dot print. Okay, I don't know exactly what is this is for. We can just, okay, look for that. So these are the only 3 things you are supposed to edit here. So this is by default it is coming. So let us not too much worry about it. So these are the things, these are the 3 things we are supposed to edit. If I do it now, if I run, now if I run, see now, okay, let me take out this. since you have set the stop time as 500 microsecond, the waveform has gone from 0 to or the scale is now 0 to 500 microsecond. Now since you not added any plot, so it is now blank. So let me start adding the, so this is my input waveform. If you can actually count the number of cycles here, you got 1 2 3 4 5. So there are 5 cycles because I wanted to see only 5 cycles. So the input voltage is a sine wave of frequency 10 kilohertz and an amplitude of 10 millivolt. So this 10 millivolt actually corresponds to 10 peak here, and this is minus 10. So this is peak to peak of 20 millivolt. So this is my input. Let me see what is the output. So this is the output. If you can see the output, actually to be very frank, what's happening is, so since the value of RD is too much, it's actually going into linear region. So what I'll do is, for the sake of clarity, because maybe you can just verify whether the MOSFET is in linear or not. Let me just go to this. Okay, what I'll do, so now since I'm not getting the expected result, so now what I should do now is, so let me just go back to this, do again .op, do this, and then you run it again, see what is VDS and VDS-SAT. Let me see this. Now VDS-SAT required is 275 millivolts, but VDS is actually, now you are just above that, what is that saturation. Now it's almost at the verge of saturation. That's why the negative peak is entering, or negative half of the waveform is entering the linear region. So what I'll do now is, I'll just slightly make this maybe 500 ohm. If I make it 500 ohm, I think now I'll be safe. Now let me just show you how much will be VDS now. VDS-SAT remains same. Can you see now VDS-SAT is 275? Can you see now VDS is 1 volt? So it is well in saturation region. Earlier it was around 2.85 at 10 power minus 1, that is, it was around 285 millivolts. Now I have 1.04 volt. Now it is better to see the output waveform. Now let me again go back and do the transient. So this is fine. Now let me run it. Now let me again see this. Let me now see this. I can see now you have, I think you, now since the input is pure AC and output is DC shifted one, you cannot properly compare the waveforms. What I'll do is, I will add one more pane. So I will make input output into different pins. Can you see now it's perfect? Now you can see, let me change this shape, change the color to, now you can see the input is increasing, output is reducing. Now it's around 1.04 volts. Now I need to find out what is the gain of the amplifier. You have already found out what is the gain of the amplifier for that circuit. Now you can verify. How do I verify? So I'll just double click on this. So when I double click, I'll get two cursors. So one clicking will give you one cursor. You can see you have got only one cursor. If you click again, you will get two cursors. So just observe here. If I click on this V in once, you can see you got one cursor. So this cursor is not enabled because I clicked only once. If I click again on the same waveform, that is this V in, I'll get one more cursor on the same. Suppose if I click on this now, if I click on this, you can see one is on input, other is on output. Okay, now this is, one is on input, one is on output. So since if you want to measure the input peak to peak, so both have to be clicked on input only. You can see now this is V in, this is also V in. I think you can make out. So cursor 1 is on V in, cursor 2 is also on V in. Now let me measure what is peak to peak. Let me just zoom this. So I will, okay, let me just properly zoom it so that I can see both the peaks. Now I'll keep one cursor on this top and the other cursor at the bottom. This is the bottom. Now this is minus 19.96. Actually this 9.98 millivolts is this cursor value, which is cursor 1, and minus 9.97 is the cursor 2 value. Actually, what does this will give you? This will give you the difference of cursor 2 minus cursor 1. That is, cursor 2 minus cursor 1 is this vertical difference, and this is the time difference. Now, the peak to peak value is actually almost 20 millivolts. Now, why it is, don't take it as minus 20. Since I placed cursor to at the bottom, it is minus. Suppose if I just reverse this, so what I'll do, I'll make this cursor to come here, one cursor. I'll make the two cursor to go up. Now you can see it is almost plus. Now it is plus. Now this is my input peak to peak. Now input peak to peak is this much. To find out the output, in order to find out the gain, I need to measure output peak to peak also. Once you set this at these maximum minimums, you can simply double click on this. The cursors will be now placed on the maximum and minimum of the output. Now you can see this is the peak to peak of output. You can see this is one peak, this is other peak. So if you can actually find out what is the gain of this, so gain is actually 109.725 millivolts by 20 millivolt, almost 20 millivolt. Can you see what's the gain then? So is the gain is almost equal to 5 point something. So now, so the way how you have to find out the gain is output peak to peak by input peak to peak. So let me just repeat. So how do I find the input peak to peak? Double click on this, place cursor 1 down here and cursor 2 at the top. Just note down what is this peak to peak, because this is vertical difference, this minus of this. And once you note this input peak to peak, you can double click on this, you will get output peak to peak. You can see it's exactly sitting on the peak, and this is sitting on the maximum minimum. So you take the magnitude of this. So why it is again minus is because this is cursor 2 minus cursor 1. So don't worry about this sign here. I can again get it plus if I just place 2 there up and 1 at the down. So you can just see that also. It's not required. So just to confirm that that doesn't have any meaning. You can see now it is positive 109. So don't worry about this negative sign. So, and this negative sign is not the phase shift. Phase shift, you can see it's clearly visible in your input and output variations. Input is actually increasing, output is actually coming down. So that's actually the negative 180 degree phase shift. I hope now this is fine. How do we find the time response? So after finding the time response, now it is time to do the frequency response. To do the frequency response, we know that we have to change this frequency from very low frequency to a very higher frequency, and we want to see how does this circuit respond for those frequencies. Does the gain remain constant? Does the gain vary? After what frequency the gain reduces, or during what range of frequencies the gain will remain constant? So since you are changing the frequency, I cannot use a source which is having a single frequency. So first and foremost thing is that I had to use this none, which is having only the AC amplitude, and let me give it as 1. So AC amplitude should be given as 1 and no other parameter should be set. This is my AC signal required to do a frequency response with a magnitude 1. Now this we have modified the source from sine wave to AC source in order to do a frequency response. So this is very important. So now let me write it for AC analysis. For AC analysis, so input should be an AC of 1 magnitude. So this is okay, magnitude. Don't worry about the English. So for AC analysis you have to do this. Now what are the changes? I have to make this change. So what are the change? I have to go for AC analysis. When I say okay AC analysis, let me also say AC analysis or frequency response. whenever you're doing frequency response, this is either it is AC response is for doing the frequency response. So now this is my waveform, the input signal for doing the AC analysis, where you are specifying only the amplitude. There is no frequency option at all, because I cannot keep the frequency constant. Now I need to change this. So I need to change this to AC analysis. Now I have to choose, you can see, compute the small signal AC behavior of the circuit linearized about its DC operating point. So of course DC operating point, whatever that has been set, it will consider that those are the DC operating points, and then we can. So now type of the sweep should be decade. So you are doing a logarithmic variation, that's why it should be decade, and number of points per decade should be 100, meaning in 1 decade to plot the graph it is taking 100 points. So let us find out, okay, if the number is less or more, what happens. So when you actually do the simulation, I'll show you one. So let us start the analysis of this circuit with a low frequency. Maybe it can be, you can start with 10 Hertz, you can go up to maybe 500 megahertz. As I said, mega means MEG. So this will go from 10 to, you cannot start from 0 frequency. 0 is not a frequency, so you have to start from a least frequency. It can be 10, 1, 50, 100, whatever, and it is 500 megahertz. Now we are done. So now that dot tran has gone, we have got dot DC, decade, 100 Hertz to 100 points per decade. This is 10 Hertz to 500 megahertz. If I run it now, okay, let me now run again. If I run, I can see this is standing going from 10 Hertz to, this is I can say 100, this is 200, 300, 400, 500. Now I have to see the response. Okay, this is the response what I have. Of course, you know, in the theory you're going to have a cutoff frequency at 102 pi Rin into Cc. You can verify what that frequency. Now if I want to find out the gain, you can click on this once, click on this twice. You have two cursors. So this is my cursor. If you can actually find out, okay, this is cursor 2. So this is cursor 2, which is now sitting on V0. It has got a gain of how much? 14.8 dBs. So if you want to know what is the gain of this, so we know that how do we find the gain of gain if you have it in dBs. So we know that it is 10 to the power of, how do we do? I think all of you know that this is if you do 10 to the power of, where is power? I'm just writing it here, 10 to the power of, open the parenthesis, how much is in dBs? It is 14.808 dB divided by 20. If you do this, so I think you can actually calculate what is that. It comes out to be 5 point something. Let me just, I don't have the calci now. Let me just try it using my mobile. Okay, let me just I request all of you to use your calcis when you are doing this. This is 14.8 divided by 20. Let me close it. I can say it's actually 5.49. This is equal to 5.49, which will be of course that will be equal to the expected gain, or of course if there is any variation or deviation from the expected gain, it's fine. So this is how you're finding the gain. So how do we find the cutoff frequency or 3 dB frequency? Now this is cursor 2, you can see this is cursor 1. Okay, when you are doing this, maybe you can just double click on this. Now it is, you are double click. Let me see whether everything is fine. Okay, it's happening. Now let me move this cursor 1. This is your cursor 1. Make sure that this magnitude difference is 3 dB. So now let me just when that magnitude difference becomes 3 dB, so then you have, are you there at 3 dB? No, I'm there, coming close to its 1.8. now it is 2.4. now it is, you are almost there. So you know, this is 3 dB corresponding to F1, this is 21 hertz. So this is my one cursor. If you can see the difference of this and this in terms of magnitude, can you see it is 14.8 and this is 11.76. The difference is almost 3 dB. So this cursor 1 frequency corresponds to 3 dB frequency, and it's surprising to see this is not coming down at all. So there is no second cutoff frequency coming. It's because in the circuit I have not edited the parasitic capacitance. So if I edit the parasitic capacitance, I'll get that also. Let me say it as CGDO equals some 200 nanofarad, and CGSO is equal to some 200 nanofarad. So these are the two capacitances that need to be added, and if I run it now you can see you're getting this. So you're getting, because of that corresponding capacitance, you have this. Now you can find the other frequency. How do I find the other frequency? Again, you place one at the top now, which is this is actually cursor 1. Of course you can put any cursor for that matter. Now you move the other cursor, so that difference is 3 dB. Again, minus 3 dB or just 3 dB depends on which one you are putting. So make sure that this magnitude difference is 3 dB. So let me just make sure that it is minus, okay, 3 dB difference. Are you there? You're almost there. Okay, now, okay, this is the 3 dB corresponding frequency. What is the corresponding frequency? You can see this is at 2.6 kilohertz, whereas this is 852 kilohertz. This is 852. So this is 1 megahertz. This is slightly lesser than that. You can see this is 900 kilohertz. It is between 800 and 900. Its exact value is 852 kilohertz. So one of the cutoff frequency was 21 hertz. The other frequency is 852 kilohertz, and the midband gain is 14.5. So this is my 14.5. So this is how you can do the frequency response. Let me just recap it. How do we do? Okay, now if it is zoomed in, if it is zoomed in like this, what you can do, you can just simply click on this. You'll get everything coming. So make sure that it's not clumsy. So you can just put them like this, so that everything is. You can just start using these effectively. Now if you want to do the dot DC operating point, it is go to this edit simulation command, do this dot op, look for different voltages and currents. Now this is Vout. These are the nodal voltages. If you want to know the details of course you should know the details of the MOSFET currents and different VGS, VDS, so VBS threshold voltage, VDS at GM. So this need to be understood. Then once you do that, I have to do a time response, which is transient. So the stop time depends on how many cycles you want to see. That depends on this time depends on how many cycles and what each cycle corresponds to. What is the time for each of the cycle, and then start saving data from 0th second and give a time step of 1 microsecond. If you do this, and of course if you do this and then try to see the input, now you can see now you're not getting an input at all, because the input is not a sine wave. So I have to correspondingly use a wave generator which gives a sine wave. Actually we have used this AC for frequency response. Now I had to use a sine source of certain frequency and certain amplitude. Now if I run it now, you can see this is your 5 waveforms. Suppose if I change the frequency to 1K, and if I don't modify the transient response, now you can see you are not getting the waveform at all. Actually this 1 kilohertz corresponds to 1 millisecond for one cycle. So since you are simulating only up to 500 on this where is the transient here? So since you are simulating up to only 500 microsecond, you are seeing only half cycle. If you want to see 5 cycles now, this should be 5 milli. So let me make it 5 millisecond, because the frequency is 1 kilohertz. Now I will get 5 seconds. So this dynamic change I should be able to do it. This is my input. You can see the output here. Again, to see it properly, because this is having pure AC, this is DC shifted, you cannot compare the waveforms. You have a different add plot pane here, and then you put one on the input, one on this pane, and other on one more pane. Then now you zoom one cycle, and then double click on this, place 2 cursors, one at the top, one at the bottom. So you have the peak to peak. Then double click on this, it will be placed on the output waveform. You can see now this is the output peak to peak. You can take the ratio, you get the gain. Again, to do the frequency response, I'll go here, I'll change this to an AC source. So this is none, the amplitude is 1 now. I'll just do this, and I have to do this should be my analysis. So I'll just take out this and then make it dot. This is equivalent to doing in the okay here. So this is exactly this. If I just say okay, if I run it, now since you can see this is also enabled, this is also enabled, it will ask for, there are multiple analyses defined for the circuit, please select one to run. You cannot make many analyses to run at a single time. So since I am having this dot as well as also this dot, it is asking which one you want to do. So say I want to do this. When you do this, you can see now you have the frequency response. Of course, input is not relevant now, because input will be a constant one. Maybe you can delete this pane in total. So I have deleted. So let me change this shape, color. I can see this is, now you have to place 2 cursors on this, one over here, the other one make sure that it is 3 dB down. So now it is, you can see this is at 3 dB. You can see now this is the frequency. Now this is in hertz, so don't take this as a frequency, because this is my cursor 2, corresponding to this is cursor 2, and place this here. So now you'll get the other cutoff frequency. Now again look for 3 dB. So this should be 3 dB. Again, don't worry about that sign there, minus or plus. So this is the other cutoff frequency, 864 kilohertz. So this way you can able to comfortably do OP, that is operating points, time response, and frequency response. Hope this will help you out. Thank you.